in section 6.2, we're going to put the algebra we learned in 6.1 to use. The section is on similar triangles, but I've started out with a little bit broader definition than the book has. Started out with the definition of similar polygons. Now this is given way over on page 500 and something. But this is what we need to keep in mind, that the notion of similarity doesn't just apply to triangles. Two polygons are similar if and only if there's a one-to-one correspondence between vertices of one and the vertices of another, so that the corresponding angles are congruent and the ratios of the lengths of the corresponding sides is a constant. The picture I've drawn here are two quadrilaterals, okay, and they are similar. And here's the symbol we use for similar. Can do better than that. Is the little what's the congruence? It's the squiggle off the top of the congruence. Okay. So A1, A2, A3, A4 is congruent to B1, B2, B3, B4. Okay, when you list them down, it's like congruence. You list them in order of the correspondence. So A1 and B1, A2 and B2, and so on. And this means a bunch of things. This is a quadrilateral, so the corresponding four angle pairs are congruent. So A1 and B1 are congruent. A2 and B2 are congruent. A3 and B3 are congruent. And A4 and B4 are congruent. Okay, not only that though, you must also, the corresponding sides must be in proportion. In other words, the ratio of A1, A2 to B1, B2 is some number, but that's the same as A2, A3 to B2, B3, okay, and that's the same as taking A3, A4 divided by B3, B4, and that number is the same as A1, A4 to B1, B4, so that the corresponding sides are in proportion. That's what we mean. Now, so if you've got a quadrilateral here, then there are actually 8 things you have to look at. You have to look at the 4 angle pairs and the 4 ratios. Okay. If you've got similar triangles, well, you're just going to have 3 angle pairs and 3 ratios. Getting ahead of myself here. I need to put something up. Now, similarity. I copied this out of the book, obviously. And it's written down here for similar triangles, but it could also be true for similar quadrilaterals or pentagons or whatever. Reflexive property means every triangle is similar to itself. Every quadrilateral is similar to itself. Every hexagon is similar to itself, and so on. Symmetric property says that order doesn't matter when you're talking about similarity. If triangle 1 is similar to triangle 2, then triangle 2 is similar to triangle 1. And these could be quadrilaterals or whatever. The transitive property is the one you probably use the most. Is if 1 and 2 are similar, 2 and 3 are similar, then 1 and 3 are similar. Okay. Need to slurp on some coffee here. My throat's a little dry. Okay. Now, let's talk about triangles specifically. If you use the definition for triangles, then it would be that 3 pairs of congruent angles and 3 equal ratios. We have a postulate here, 6.1. It says the 2 triangles are similar if and only if 3 angles of one are congruent to the 3 angles of the other. In other words, you don't have to check everything, you just have to check that corresponding angles are congruent. A, B, C, and D, E, F are congruent triangles if and only if A and D are congruent, B and E are congruent, C and F are congruent. Now, this is a postulate. which means it is something we accept as truth without proving it. You don't have to. What I mean by that is many books show that prove that this is true. In other words, you don't have to assume it's an apostolate. You can prove that it's true based on what you already know. It just takes a long time. So we're going to do something that we've done several times already, is we're going to accept this as a postulate so we don't have to prove it. So we don't take a week or so developing an extra framework here and taking a while to prove it. Okay, so I'm going to do some problems here, and this is and all we've got to work with so far is that congruent pairs of angles. Problem number 28, page 316. This was a very interesting picture. It took me a while to think about this. Show the triangle ABC is similar to the small triangle A prime, B prime, C prime, where X represents the measures of the angles. Now what I've done here is I've put in some extra stuff in blue. Some items that weren't written down beforehand, but it seemed to me you needed some names of some of these points and some sort of description for some of these angles. Okay, so let me see what I can do with this. Let's take a look here at, there's a quadrilateral E, C prime, E to C prime to F to C. Actually, before I do that, back up a little bit. If this angle is X, right here to the left, then what's the angle on the right-hand side? Well, these two angles make a straight line, so this is going to be 180 minus X. As is this angle here, and this angle here. Okay. Now let's take a look at the quadrilateral E, C prime to F to C. So it's this thing over here. If you add up, let's let little c be the measure of this angle. Here. Okay, so it's the measure of the angle at C. If you add up all those angles, so let's start at E. Angle at E is X. The next angle we come to is this guy here. So we'll take the angle of this is E, C prime, F, plus the next angle we come to down here is 180 minus X. And then we have angle C. And when I add up all those angles, I should get 360 degrees. It's one of the formulas we had a long time ago, that the angles of a polygon, n-gon, add up to 180. No, n minus 2 times 180. Yeah. Okay, so what do we have here? We add these up. This x and this negative x cancel. Okay, I'm going to subtract 180 as well. So I'm left with the measure of angle E, C prime F plus C is 180 degrees. So okay, this is 180 degrees minus C. So what's that measure? That's 180 minus C. So this is enough to tell us that the measure of angle B prime, C prime, A prime is little c. It's this guy. Let's do the same thing with the quadrilateral up here at the top, which is, let's do G, B prime, E, B. Okay. Look at the angles there. X plus whatever this thing is. The measure of angle G GBE plus 180 minus X plus the measure of angle B, which I'm calling that's going to be 360. Okay. The X's cancel. Subtract 180. The measure of angle GBE plus this thing here is 180 degrees. So the measure of angle GBE is 180 degrees. Whoops. Minus B. Okay. So that's this thing right here, 180. It's kind of small. It's this angle, so that angle is going to be B right there. So the measure of angle C prime, B prime, A prime is B. And the same sort of reasoning gives that the measure of angle B prime A prime C prime is little a. So that tells that these two triangles are similar. Okay, you might want to roll the picture up a little bit more. Actually, it could be drawn a little better too, but this is pretty much what it looks like in the book. They didn't give you much space, and there may be another way to work this, but I sure couldn't figure it out. Okay, if you know two angles of a triangle, you automatically know the third because they must add up to 180. So we can actually get away with a little less. We don't have to prove that all three angles are congruent. We can just prove if this angle and the way I've got it drawn, this angle are congruent, and these two are congruent, then of course we know that C and F left over would have to be congruent as well, which means all I have to do is to show that two pair of corresponding angles are congruent, and that would show that the triangles are similar. I'm going to use that idea on problem number 29, and I'm supposed to prove this, but I'm not going to do a real great proof. Well, I mean, I'll say everything. I'm not necessarily going to write it all down correctly. Okay. So I've got two triangles here, ABC and A prime, B prime, C prime, and the corresponding sides are parallel to each other. That means AB and A prime, B prime are parallel. So what I'm going to do is I'm going to look at not the line segment A prime, B prime, but extend it in order to make a full line. Okay. So I have AB and then A prime, B prime, which I'm extending until it intersects the big triangle. Okay, so those two things are parallel. So AB and A prime, B prime are parallel. That means this angle and this angle are congruent corresponding angles formed when two parallel lines are cut by a transversal are congruent. Similarly, BC and B prime C prime are parallel lines, and they're cut by this red transversal. So this angle and that angle are congruent. So the angle B and the angle B prime are congruent. Now the same sort of thing happens down here in the A corner. AB and A prime B prime extended are congruent, are parallel, excuse me, and they're cut by transversal AC. So that means this angle and that angle are congruent because they're corresponding angles formed by parallel lines. Now, AC and AC and AC, A prime C prime are parallel, and they're cut by the red transversal, which means that this angle and that angle are congruent. So if A is congruent to this and this is congruent to A prime, then angle A is congruent to A prime. Okay. That's a real quick justification. It's not a good proof. It's a sketch of the proof. Extend the sides of one of the little triangles. Look at how it intersects the sides of the big triangle, and you can get quite easily that two pair of congruent angles, and then apply 6.4. Okay, 6.5 is a right triangle version of 6.4. Now in 6.4 you needed a pair of corresponding congruent angles. Well, if you've got right triangles, you already know that the right angle parts are congruent. So you just need one more pair of congruent angles. So in A, B, C, and D, E, F, if C and F are 90 degrees, so if it's a right triangle and A is congruent to D, then A, B, C, and D, E, F are congruent. Okay, it's just a right triangle version of the previous one. Now we come to problem number 9. We'll use this corollary. It's actually a fairly long problem, a little bit longer than some others. Okay, here we have a couple of triangles. Actually, there's two right triangles. So they are, this is supposed to be a right triangle. Let me make it all over again. Okay, let's use straight lines. Something like that. Okay, this is E, F, R, and G, H, I. Both of these are right triangles, and they share this angle of I. So that means they are similar. Well, let me do, tell you what, let's do this one first. This question mark down here, HI, I could have done that without doing anything about about similar triangles, because it just happens to be a right triangle down here. So let's do this. HI, it is a leg of a triangle. 3 is the other leg of the triangle, Pythagorean theorem says they add up to hypotenuse squared. Okay. So hi squared plus 3 squared equals 6 squared. 3 squared is 9. That's what this number is supposed to be here. That's supposed to be a 9. Okay. Hi squared equals 27. 27 is 9 times 3, and I can take the square root of 9. 3 square root of 3. So they don't want decimals on this guy. So let's do that one. Okay. Now let's do some similar triangles. Okay, in the big triangle, I have a 5 over here. In the little triangle, I have a 3, a 6, and a 3 square root of 3. So when I have similar triangles, I have sides, corresponding sides are in proportion, which means the long vertical leg divided by the shorter vertical leg is the same as the long hypotenuse. I don't have a label for that. That's EI divided by the short hypotenuse, which is 6. Okay. So multiply both sides by 6. That's going to be 10, and that's EI. That's not what they asked for. This is 4. 10 minus 6 is 4. And we also have some sides that are in proportion that are legs. The tall vertical leg divided by the short vertical leg should be the same as the long horizontal leg divided by the short horizontal leg. So multiply both sides by 3 square roots of 2. Square root of 3, excuse me. Got it wrong there too. Okay. Times 5 over 3. 3's cancel. 5 square root of 3 is Fi. So that's this whole distance. So FH five square roots of 3 minus 3 square roots of 3 is 2 square roots of 3. Okay, so a bunch of computations on that one. Some more similarity theorems. Now here we've got, what else can you get away with? In other words, similar triangles have 3 pairs of congruent angles and 3 ratios of sides that are all equal to the same thing. Well, we don't have to do all 3 pairs of angles. We can only do 2 pairs of angles. And the SAS similarity theorem says you can even get away with 1 pair of angles if you have, so we just get away with 1 pair of angles if you have some proportionate sides that make up the angle. Okay. This is not a theorem I remember ever seeing before. And I'm kind of sorry the book says the proof is omitted. I think they're weenies. I'm not going to do an example of that. They have a nice one in the text on page 311. The right triangle version of this is the, or if you're talking about the legs, then the included angle is a right angle, which obviously are uh, congruent. So if the corresponding legs are in proportion, then you have similar triangles. And one last theorem here is side-side-side similarity theorem. Go all the way back to our very first definition of similar polygons. You had similar angles, congruent angles, and the sides were in proportion. And the first postulate we had was, for triangles, all you needed to know was if the angles are congruent, then the sides will automatically be in proportion. Well, what we're saying here is if the sides are in proportion, the angles are automatically congruent. And the example to work here is number 2. Okay. And I didn't write down all the directions here. You're supposed to figure out what triangles are congruent and why. Well, here on number 2, triangle FGH is similar to triangle IJK. And the reason is, well, to take a look at the corresponding sides. FG. Okay. FG corresponds to IJ. 1.5 over 3 is 1/2, 1.2. Okay. GH. The corresponding side to that is KJ. 2.5 over 5 is 1/2. And finally, FH and IK, that ratio is 2 to 4, that's 1/2. These are all the same. So this is similar by side, side, side. Two more problems. 19. Let ABCD be an isosceles trapezoid with diagonals intersecting in point E. Prove that triangle AED is congruent to triangle CEB. So use whatever tools we have here. First off, usually books don't do this, but we don't need isosceles in this case. All we need is that it's a trapezoid, and that means that BC is parallel to AD. Okay. All right. And again, this is not going to be a really great proof. It's going to be a real quick sketch. Angle AED is congruent to angle CEB. That's because they're vertical angles. Angle CBE is congruent to angle ADE, okay, because I have two parallel lines cut by transversal alternate interior angles. Parallel lines. Similarly, angle ECB is congruent to angle EAD for the same reason. This doesn't. The three pairs of angles, these two these two and these two are all congruent. So triangle AED, nope, it's not congruent. It's similar to triangle CEB. Pretty simple. And nowhere did we use the isosceles characteristic. Because nobody says that things have to be same size or same length, just as long as, I mean, unless they're parallel here. So the lines are parallel. Now the last one. This is a little bit of a mess, but it's a good problem. Sawdust is dropping from a conveyor belt onto a pile. Okay, so we've got some sort of conveyor belt here, and the sawdust comes out of this, and it makes a pile. Okay. And it's an approximate shape of a right circular cone. I will not be able to draw this very well at all. I can draw it really well on paper, but we have some sort of right circular cone. Now the thing about sawdust is it's falling off a conveyor belt or sand or gravel. Because of the nature of the material, it will always form a cone that's the same shape. In other words, the cone is not going to flatten out. As time passes, it's not going to flatten out and get real wide. Okay, and it's not going to get real tall and skinny. Okay, because of the nature of how the particles stick to each other, it's always going to be a cone about this same shape. Okay. So, at one time, that's going to be right now. The height of the cone is 5 feet. It's 5 feet, and the circumference is 25. Okay. Now, the stuff builds up more. Now that is supposed to be a cone. And the large cone is, well, I don't know what the height is. H, let's call it H. And the large cone circumference is 62. Okay. So the large cone is something like this. This is H. Okay. Now, it says use similar triangles. Well, I don't see a triangle here unless we do the triangles that go along the base of the cone. Now, in those cases, your triangles are going to have a height. So the small one's going to be 5, the big one's going to be H. And they're also going to have a width here, which has to be the radius. Okay. So from this guy, the circumference Need a radius. Okay, so for this guy, the circumference is 25. And remember what circumference is? It's 2 pi r. So 25, 2 pi equals r. Okay. For this guy here, circumference is 62. 2 pi r. So 62 over 2 pi equals r. We could convert these to decimals, but I think in the process I would round off and lose some accuracy. So I'm just going to hold on to these funny numbers. And I can't do a whole lot. I mean, I can reduce this one a little bit. And make it 31 over pi. But otherwise, I can't reduce these too much. Okay. Now, what are we looking at here? We're looking at, we need some sort of equation here. If these are similar triangles, if this little blue triangle here is similar to the red triangle, then corresponding sides should be proportional. In other words, the tall height is to the short height as the big radius is to the small radius. And let me rewrite the right-hand side. I'm dividing fractions, so I want to invert and multiply, and the only thing that cancels off h over 5 is the pi's cancel, 62 over 25. So multiply through by 5. The 5's cancel. H is 62 over 5, which is 112.4 feet. And we're just about ready now. That's the height of the sawdust at the later time. How many cubic feet? Okay. And the volume is 1/3 pi times r squared. We're looking at the big R now. Times h. 12.4. And let's see what we got here. Volume equals 1/3 pi times r 30. So we have 1/3 pi times 31 divided by pi squared. So that's radius squared times the height. (1264,369) round to the nearest tenth, so 1264.4. And this is cubic feet. Everything here was feet. Okay. I don't think you can read that. Try that again. (1264.4 cubic feet). Okay. Well, that's it in terms of this section. The next section on similar triangles, on similarity, has some interesting applications. Lots of stuff with parallel lines. Then the section after that is on right triangle trigonometry, because if it wasn't for similar triangles, trigonometry wouldn't work. We're going to skip that. I'm assuming you can do section 6.4 and 6.5 with trigonometry stuff. So in other words, we've got one more section in this chapter that we'll cover, and then we'll get into chapter 7 and talk about circles.